Hello everyone. In the previous session we have discussed the concept of simple function. So we need a few more information regarding simple function in order to prove next theorem. So let me repeat once again. Any function which is defined from E to R is said to be simple only when f takes a finite number of values, right? Further, we can express any function as it's in canonical form, in the sense, as we already know that any domain E can be expressed as union, that is countable union, right? So this is what the meaning of countable union is. And further, all the EIs will be disjoint, that is, if you are going to take intersection of any two sets in this particular set, that will be null set. That is the meaning of disjoints of a set. So let me define once again. F is said to be simple if it take finite value, and further any set E can be expressed as union, that is countable union of all the sets. Further, whatever the sets you have inside, they will be disjoints. So meaning is intersection of those two sets, any two sets will be that is different. For I is not equal to j, meaning is EI is different from EJ. If you are going to take any two different set, so the intersection of those two sets will be null set, meaning is they are clearly disjoint. Further, this function can be expressed in its canonical form. Canonical form in the sense we can express f as a linear combination of certain function. So f can be written as, for any constant a1 into chi of e1. This symbol is called as chi. Fine. Chi of e1 plus a2 into chi of e2 plus so on plus an into chi of en. Fine. So this is the meaning of linear combination of a given function f. So further, this entire thing can be written as summation I is equal to 1 to n ai into chi of ei. You have to remember this canonical representation of a simple function. This is called as canonical, that is linear combination, one and the same. Canonical representation of a function, simple function. Clear? And further, if I can write this as directly, if f is a function defined from a to r, it implies that r is simple, or f is simple. Simple implies that if f is simple, I can directly write f as I is equal to 1 to n ai into chi of ei. Meaning of simple function is, canonical form of a simple function is, the minute when I said f is simple, I can apply the canonical representation. Further, next we can define elementary integral. Elementary. This is all just basic definitions that we are using in a further theorem. So elementary integral of a simple function. It is defined as, suppose, meaning is elementary integral in the sense, suppose as I already told you, simple function, if f is simple function, I can express this in a form of canonical representation. So if that was the case, if you are going to take integral of that function f, we can write this as summation I is equal to 1 to n ai. This chi of ei will become measure of ei. Whatever the set you have here, whatever the domain you have, so you have to write the same domain, measure of ei. So this is the elementary integral of a simple function. You have to remember this. So I will just give you an overall picture. See, if f is a simple function, I can write this in its canonical form as a into chi of ei. Further, if you are going to apply elementary integral for this, I can write this as summation I is equal to 1 to n ai into measure of ei. Suppose if you have, in place of ei, suppose if you have something like ai, you can replace ei with measure of ai. So nothing will change, everything will be same. Instead of ei, I have to write ai. So this is the basics regarding canonical representation and elementary integral of a simple function. Anyhow, I will send you the notes. Next, let me prove the theorem by using this representation. So here is a theorem, and it is very important. It is asked in the year 2016. Fine. Now, if pi and psi are any two simple function, then which is defined in a domain E or measurable set E, then we can prove these three statements are true. Now, in the statement itself, it is given pi and psi are two simple functions, right? So just now I have told you, if f is any simple function, we can express it in form of canonical representation. See here, if f is a simple function, we can write it in a canonical form. So I am going to apply the same here. So pi and psi are two simple function. Given that, let me prove. given that pi and psi are simple function. So as per the canonical representation, how can I write? This implies pi can be written as canonical representation ai into chi of ai. Let me take this as ai. I is equal to 1 to n. And further psi will be, let me take other form. Since I have chosen n here, I have taken m. And instead of ai, let me take bj and chi of bj. Fine. So since f is simple, I can write it in the form of canonical representation, and that is what I have done. Where ai is set of all the elements which is in a measurable set E, such that pi of x is equal to ai. And similarly bj will be set of all the elements in domain such that psi of x is equal to bj, where I ranging from 1 to n and j ranging from 1 to m. It is given. Fine. And moreover, I have already told you while explaining the canonical representation, what are the elements that you are going to choose in this set? They are disjoint. That is what I have said. See here. Here the element is ei, that is measurable set is ei. So ei can be expressed as finite union, and moreover they are disjoint. So whatever the set you have here, they are disjoint. Similarly, here in place of ei, I have ai. So I can write ai for any suffixes ak will be disjoint, that is null set. And further here also same, that is bj intersection br will be null set. Why? Because they are clearly disjoint. Further we can express a as, I'm just applying the definition of a simple function. That is not what I have explained. See here, you have to remember this. This is the canonical representation. ei is a set which can be expressed as finite union. That is, any measurable set E can be expressed as finite union of all the ei's, and moreover whatever the elements we have inside, that will be disjoint. That is, intersection will be equal to null set. And I have applied the same thing here also. See here. So I have taken it as ai into chi of ai. So ai, instead of ai, I have ai. So ai can be expressed as e can be taken as union of ai. So in place of here I have bj. So I can write this as j is equal to 1 to m, bj as e. And moreover I have chosen they are disjoint as per the definition of canonical representation of a simple function. Now hope so it is clear. If you know that definition, you can apply directly. Now this is the basics that we already discussed. Now let me prove first one. Fine. So first one, I have taken any constant for any real constant a. So let me write for any real constant a. We already know that if pi is simple, if you are going to multiply any simple any real constant to a simple function, again it will be simple function only. Simple function. That is, I am just trying to repeat once again. If pi is simple function, if you are going to multiply any real constant with the simple function, again resulting will be a simple function. So as I already told you, if f is a simple function, we can write it in a canonical form. Now a pi is a simple function, so I can write a pi as its canonical form, right? I is equal to 1 to n, a as it is. Now pi can be written as ai into some chi I, a into some chi of ai, right? That is what pi is, ai into chi of ai. A is constant, I have taken it outside. Now let me rewrite this as, I can write this as summation I is equal to 1 to n, a into ai, I'll just write together, into chi of ai. Fine. So a pi I have. Now what we need is integral. Just now I have explained elementary integral of a simple function. You go through that. See here, elementary integral of a simple function. If you are going to integrate it, so whatever the set you have to take measure for that. So I am going to apply the same property here. Let me apply elementary integration. So you will get I is equal to 1 to n ai. Here the set is ai. So I have to apply measure for that. Removing chi, and I have to apply measure for ai. That is what the definition of elementary integral is. Now how can we write this as? Now I can summation is for a suffix I. Since first term is independent of I can take a outside, so that I is equal to 1 to n ai into measure of ai, right? So I can write this as a into pi. Clear? Now you can clearly note that this will be an integration of a pi, simple function pi, right? I'll just explain once again. See here, suppose if pi, what I have chosen, pi as ai into chi ai. I'll just write here. See here, suppose if you're going to take elementary integral of this, what I can write this as summation I is equal to 1 to n ai as it is. Instead of chi of ai, I have to write measure of ai. Right, that is what the meaning of elementary integration is. So integral of pi is ai into measure of ai. So that is what I have here. So I can write this term as integration of pi. I have written a as it is, and I have written this as integration of pi. So and that is what I have to prove is integral over a into pi is equal to a into pi. Sometimes they will mention domain here, that is a measurable set e here. Fine. So hence we have obtained the proof of first one. Now similarly let me prove the second one. Second one is, that is sum. So I'll just prove here. Second one, what we have, integral over pi plus psi, we have to prove it as individual sum. That is what we need to prove is second one, and I have just written a statement. Now let us come into the proof. So as I already given in the statement, they are pi and psi are simple function. So let me take pi plus psi. I have already assumed at the beginning itself. So first one proof is right from here. This is basics which will be applicable for all the three statements. So pi and psi I have assumed in such a way that pi is equal to this term and psi is equal to this term. Now I am going to add those two terms, pi plus psi. I'll just do here. See here, pi plus psi I am going to add, so that I can write pi as I is equal to 1 to n ai into chi of ai, plus psi as summation j is equal to 1 to m bj into chi of bj. Fine. Now I can write, I'll just simplify here only. So I can write these two terms as I'm going to combine both the summation, so that I can write a summation. I'll just combine both the summation. I'll just write here summation I is equal to 1 to n and summation j is equal to 1 to m ai plus bj into chi ai into chi bj. What I have done is I have just written the summation terms one side, and I have added the terms which is inside the summation. Fine. Now I can write this as further pi plus psi will be equal to summation I is equal to 1 to n summation j is equal to 1 to m ai plus bj. This can be written as chi of ai intersection bj, one and the same. Instead of writing individual, I am going to combine this, so that I am going to take a common term. So both the terms can be written as single term. So let me take this as equation 1. Why? Because the set ai intersection bj is finite collection of mutual disjoint set. That is what I have taken at the beginning. See here, ais is also disjoint and bj is also disjoint. If that was the case, disjoint in the sense there is no common element, so that I can take intersection of both in order to cover both the elements of a set. Clear? So let me take that as equation 1. So clearly I can express ai intersection bj as e, union taken over all j. That is what the definition is. See here. Here in place of ai I have, in place of ei in the standard definition I have ai. So I can write e as union of all the ai's. Here also instead of ai I have bj. So bj can be written as union of all the bj. Similarly in place here you have ai intersection bj. So I can write e as union of all ai intersection bj. Fine. Now one is the canonical representation of a simple function pi and psi. Right. So equation 1 you can note that this is the canonical representation of pi plus psi. Right. So see here, I'll just show you. Here pi is the canonical representation. This one is canonical representation of pi. This is canonical representation of psi. Now this is of the form canonical representation of pi plus psi. Right. Now let me write pi plus psi. I'm going to take integral over equation 1. So equation 1 become, when you apply the integral, elementary integral, so this equation you will get I is equal to 1 to n, j is equal to 1 to m, a I b j, chi of ai intersection bj will become as per the definition of integral. See here, that is what elementary integral says. Whenever you have chi ei, you can write m of ei when you are going to take integral for this equation. Similarly, apply integration for first equation. So in place I have this. So I have to take measure of ai intersection bj. Clear? Now I am going to split this summation. You can look at this equation carefully, so that I is equal to, I can write this as I is equal to 1 to n. Now I am going to split the terms containing ai. I'll just write here measure of. Now let me write one more step if you want. So I'll just write here. Now I'll take summation j is equal to 1 to n measure of ai intersection bj, plus I'm going to split bj now. It is just like a what we say, a multiplication. Bj summation I is equal to 1 to n measure of ai intersection bj. What I have done is I have splitted the summation for both the terms. This is one term, and along with ai this is one term. So summation with the first ai and second with j. So that is why when I am choosing bj first, so I have taken j outside. When I am choosing I have taken I outside, and rest of the things is as it is. Fine. Now I can write this as I is equal to 1 to n. Now look at this step carefully. ai as it is. Now I'm going to take measure outside, that is m outside, so that when you're going to take measure outside, as per the property, summation will become union. That is what, when you have union, if you're taking measure you have to take summation. When you're taking measure outside, the summation will become union. Union j is equal to 1 to m ai intersection bj, right? So this is one term, plus here also I'll do the same, summation j is equal to 1 to m bj I'll keep as it is. Now I'm going to take measure outside, so that summation will become union I is equal to 1 to n. Since I have j, right, so you have, whenever you have j you have to write m, whenever you have I you have to write n. I is equal to 1 to n. I can write this as ai intersection bj. So this is one term. I'm just repeating once again. What I have done is I have taken, instead of measure inside, I have taken reverse, that is measure outside. When you are going to take, summation will become union. If you are going to take measure inside, union will become summation, one and the same. Now let me simplify this step. Summation I is equal to 1 to n ai I'll keep as it is. Now I'll just arrange this in one. Let me write one more step. So I'll write ai outside. Why? Because union I have for j. So since I have ai which is independent of union term, so I can take this outside. Intersection, now I'm going to combine union with bj. Why? Because it is summation ranging from, that is values ranging from j, so it is for bj. Similarly, you can note that here I have term ai, so j is independent of I, so I can write bj outside. So I can write this term as, first let me write this, bj into measure of, I'll just combine union with ai. Union I is equal to 1 to n ai intersection with bj. Fine. And one more hint is that you have to remember, whenever you are going to take intersection with two sets, I have just told you at the beginning, very, what we say, a blind method, but remember, when you are going to take intersection with two sets, one is large and another is small, always you will get a smaller set. Intersection will be always a smaller set. I'll give you a simple example. For example, let me do here. Suppose if a is equal to 1, 2, 3, 4, 5 and b is equal to 4, 5. Right? So if you are going to take intersection of these two elements, these two sets, you will get 4, 5. Anyhow, it is smaller only. Fine. Suppose if you have b intersection a, then also you will get 4, 5 only. That is, when you are going to take intersection of two sets, you will get a smaller set. Similarly, here also, since you are taking intersection with this set and this set, since it is only one set, but it is union of all the sets. Here also, this is small set, this is larger set. So as I already told you, when you are taking intersection, you will get smaller set. So this is the smaller set here. In these two, this is the smaller set. So this step can be written as summation I is equal to 1 to n ai as it is. Now among these two, smaller set is ai, so I can write ai plus summation j is equal to 1 to m bj as it is. Among these two, smaller set is bj, so I can write measure of bj. Clear? Now you can clearly note that ai into measure of ai is none other than integral over pi. Similarly, this is integral over psi. Right? Why? Because at the beginning what I have assumed, you can see here, pi, integral over pi is none other than ai into measure of ai. Similarly, when you are going to take integral over psi, what you are going to get? Summation I is, this is all standard, you have to remember. Summation a bj into measure of bj you are going to get. Right? So that is what we have obtained here. See here. ai into measure of ai. Bj into measure of bj is none other than integral over psi, integral over pi. And whatever you have in the LHS is measure of pi plus psi. So measure of pi plus psi is equal to measure of pi plus measure of psi. And that is what we require to prove is. Hope so it is clear. The only thing is you have to remember the canonical representation and manipulating the terms. Fine. Now we have a last one, that is pi plus psi is equal, pi is less than or equal to psi almost everywhere. Then we have to prove that pi is less than or equal to psi. So only left is third one. So let me prove that. So I'll just write the third statement here. Third statement, what we require to prove is pi is less than or equal to psi almost everywhere. Then we have to prove that integral over pi is less than or equal to integral over psi. So proof is quite simple. Let me explain here. Now, given that pi is less than or equal to psi, right? So if pi is less than or equal to psi on any domain E, we can write psi minus pi is a positive number, right? For example, I'll give you one example. See here, suppose if 5 is less than or equal to 6, this expression is true. Obviously, if 5 is less than or equal to 6, we can write 6 minus 5 is always positive, right? 6 minus 5 is 1. Anyhow, it is positive only. Similarly, see here, if pi is less than or equal to psi, what I have written? Psi minus pi is greater than or equal to 0. Obvious, that is positive number. So I can write, if this is true, I can write this is also true. Now let me consider psi minus pi in its canonical representation. Let me take this as I is equal to 1 to n ai into chi of ai, right? So I have taken a canonical representation for psi minus pi. Now let me take a elementary integral over this. So I have already told you, when you're going to take elementary integral, you have to remove chi, you have to take measure for the given set. So let me write I is equal to 1 to n ai. In place here you have suffix associated with chi is ai. So you will get measure of ai as we already done. Fine. Now you can clearly note that measure of any set is positive, right? So measure of ai is greater than or equal to 0. I can write this is positive. So if this is positive, obviously this is also positive, right? So I can write psi minus pi is also greater than or equal to 0. And moreover, just now in the second case, what we have proved, see here, pi plus psi will be equal to pi plus psi. So it will be applicable for subtraction also. If pi minus psi we can split that. So thereby I can write this as integral over e psi minus integral over e pi is greater than or equal to 0. And this is same as integral over e pi is less than or equal to integral over e pi. Just like this concept. Suppose if you have difference is greater than or equal to 6, like 6 minus 5 is greater than or equal to 0, then I can write 5 is less than or equal to 6. See here, 6 minus 5 is greater than or equal to 0, right? In the sense it is positive. So let me take 6 as pi, 5 as chi, just for pi less than or equal to 6 in the sense psi. So that is what I have done here. I have taken integral over that. So what is the obtained thing? I'm sorry, this is psi, right? This is psi. So pi is less than or equal to psi, and that is what I have proved. Hope so it is clear. So this is what the third one is. Fine. So this is the theorem based on canonical representation of a simple function. So whatever I have done in this session, notes will be forwarded in the group. Please copy the same. So in the next session, let me continue with the Lebesgue integral of a bounded function, and it is also very important. So please go through the notes. Further, if you have any queries, you can free to ask me. Thank you.